This is a quick video of the 9.5 notes. The topic is polarity, and the essential question, what is the difference between a polar and nonpolar covalent bond? By the end of this lesson, you should be able to determine whether a covalent bond is polar or nonpolar based on what kind of atoms it's made from. And you should be able to locate and write formulas for diatomic elements, and then explain how these polar and nonpolar bonds can affect a molecule's state of matter. So the first thing I want you to do is to think of the word polar. What do you think of when you hear the word polar? Here are some things that came to my mind. Um, Polar bear, polar opposites, polar magnet, polar ice caps. Um, Polar express was one that I heard from another student. So most of these words um, have a meaning that draw your mind or your image to things that are opposites, except for maybe polar bears, and they're polar because they live at opposite ends of the globe. In chemistry, our definition of polar is going to be having oppositely charged ends. And that's one of the unique features of covalent bonds. They can either be polar, have opposite ends, have oppositely charged ends, or nonpolar. And nonpolar means that they don't have those oppositely charged ends. Here's an example of a polar covalent bond. Here's chlorine and hydrogen sharing electrons. Remember, chlorine has 7 valence electrons. Hydrogen only has 1 valence electron. It only has 1 electron, period. And so when they share electrons, because chlorine has so many more protons than hydrogen, the electrons that are shared, so here's chlorine's electron, here's hydrogen's electron, end up on chlorine's side of the molecule more time than they spend on the hydrogen's end of the molecule. So this is accomplished when we have two different kinds of nonmetal elements. And because they're different, they have different numbers of protons, so different amounts of pull for the electrons. And since chlorine's pull on the electrons is stronger than hydrogen's, the electrons spend more time on chlorine's side of the atom. Now, that force of attraction isn't quite strong enough for chlorine to strip hydrogen of its electron and become an ion. They're still sharing. It's just that the electrons are spending a little more time, well, a lot more time with chlorine than they are over here with hydrogen. Keep in mind the electrons are constantly moving, so every once in a while, one of these electrons will swing over here to be with hydrogen's proton as well. All right, so this is another way to picture that covalent bond. The electrons are shared unequally between the two atoms. So basically what happens is we get this pool of electrons over here. So we've got 8 electrons hanging out around chlorine and no electrons on this end hanging out around hydrogen. That makes what we call a partial positive or partial negative end of the molecule. And it's important to remember that this is still neutral. We still have the same number of protons and electrons, but because they're hanging out on this end of the molecule more, it tends to make this end of the molecule slightly negative. And that's what this little symbol stands for. It's a lowercase delta from the Greek alphabet, and it stands for slightly negative. Again, overall positive, but this end or this pole has a slightly negative charge, and this one has a slightly positive charge. Keep in mind that those hydrogen and chlorine protons aren't going anywhere. They're buried deep inside the nucleus and they're not moving. It's only the electrons that are moving. So we either end up with a pool of electrons on one end that makes it slightly negative, or we have a lack of electrons on this end, making it slightly positive. Here's an example of a nonpolar covalent bond. Now, with the polar covalent bond, we said it was two different kinds of atoms. And because all of the atoms on the periodic table have a different number of protons, the amount of pull on the electrons between two different atoms is always going to be different. For a nonpolar covalent bond, though, we're looking at two atoms that are the same. And this is for a purely nonpolar covalent bond. So it's made by joining atoms of one kind of nonmetal element, and both atoms have an equal attraction for the valence electrons. In other words, they have the same electronegativity. That was the word that we used to describe that the attraction that the nucleus has for electrons in a chemical bond. So basically, these electrons end up hanging out right in the middle of this tug of war for the electrons. And again, they're constantly in motion. So every once in a while, this electron will come hang out over here and it'll hang out over here. But most of the time, or the average location for those electrons is right in the middle. And so you can see we don't have a positive and a negative end. We don't have opposites. Both ends are positive. And so this is what we call a nonpolar covalent bond. The way we would write the formula for this is H2. Oxygen will do the same thing, O2, chlorine, bromine, iodine, and fluorine will also form what we call, diatomic elements, or two atoms of the same element bonded together. Okay, so now let's take another look at how those could be pictured. So here's our hydrogen again. And notice we don't have one end with a higher density or pool of electrons than the other. Here's an example of oxygen. If we look at their valence electrons, both have 6 in the outer shell. So by sharing this pair of electrons and this pair of electrons, oxygen now has 8 valence electrons in each one of its shells. And so it's very stable. Oxygen without those 2 electrons to get up to the 8 valence electrons is not stable. And so if you can picture in the air a gazillion oxygens, and they're constantly moving, so they're going to bump into each other. If one oxygen bumps into another oxygen, they will immediately pair up because they're so much more stable together than they are apart. Okay, and again, we call these diatomic elements. Remember, elements are made out of one kind of atom. So anytime you see one element or one kind of atom, even if it has a subscript, we're still going to call that an element. Diatomic means two, di means two, atom elements. Two atom elements. And this is going to be important when we start writing chemical equations, which is our next unit. And so it's important for you to remember that if you are reacting with a chemical, let's say sodium, which is a metal, with oxygen, that oxygen is going to come from the air and it is going to be paired up. So oxygen from the air as an element is always going to exist as O2. All right. There are 7 elements on the periodic table that are considered diatomic. And if you look on your periodic table, right next to the name of the element, so kind of up in the upper right-hand corner, right here, there's a little black square with a 2 in it. And the key clearly tells you that means that that element is diatomic, meaning that in nature, the only way we're going to find nitrogen is as N2. Okay, so there are 7 of them: hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. And the way I remember this is the rule of 7. Diatomics follow the rule of 7. Okay, so Hydrogen is kind of doing its own thing over here. It always is. But rule of 7, there are 7 elements on the table that are diatomic. And except for hydrogen, if you go over to element number 7, nitrogen, and make a 7, those are the diatomic elements. All right. So in an equation, you would always write N nitrogen as N2, oxygen would be O2, F2, Cl2, Br2, and I2. Now, because they are made from one type of atom and elements are made of one type of atom, we name these like we would name any other element on the periodic table. We do not use prefixes. So that's not dihydrogen, it's just hydrogen. Not dinitrogen, it's just nitrogen. All right, one more quick point, and that is that these molecules that have or don't have polarity affects the way that they interact with each other. And so intermolecular attraction is the attraction between two molecules. And if we have two molecules that are not polar, there's nothing between them that will attract. So it's like two magnets, and what these lines represent is the force of attraction between them, the magnetic attraction. And you can see that the farther that those magnets get apart, the weaker and weaker the attraction gets. So there's very little attraction between two non-polar molecules, as long as they're made from the two atoms that we're learning how to name. All right, and then over here we have hydrogen and chlorine. Notice that because they do have an excess of electrons, making this end slightly negative and this end slightly positive, that the attraction between these two is greater. There's a stronger attraction. Okay. Now, where we can apply this is when we take a look at the states of matter for particularly the diatomic gases. Okay, if we look on our periodic table, the one that I gave you has little balloons, which stands for gas, in all of these except for bromine and possibly iodine. But that's because bromine tends to be a liquid at what we call standard temperature, which is actually 0 degrees Celsius. At room temperature, that's just warm enough to make it into a gas. And then iodine also at its surface vaporizes very easily. And then we know hydrogen's a gas as well. And gas particles are gas particles because they don't stick together very well. They're in constant motion, moving really fast, and they have no attraction for one another. So that explains why our diatomic elements are primarily gases. Solids and liquids, on the other hand, are attracted to one another. Solids more than liquids. Liquids can still move past one another. But if we take a look at a lot of the polar molecules, when two of those polar molecules come in close contact with one another, they can be liquids or solids at room temperature. Now, a lot of them are still gases because there are other factors besides the polarity of the individual bonds that affects whether or not they're attracted to each other. And one of those effects is the geometry or the shape of the molecule, which we're not going to get into. All right, so that takes care of the 9.5 notes, and have a good day.